All right, let's get right into it. Today, we're going to pull back the curtain on the secret sauce behind some of the world's most powerful AI models. We're talking everything from Google's own Gemini to Anthropic's Claude. We're going to explore the incredibly specialized hardware and the brilliant software that have to work in perfect harmony to make it all happen.
So to really wrap your head around the sheer scale we're dealing with, just look at this number. Over 1 million. That's how many of Google's tensor processing units, or TPUs, the AI company Anthropic is using. We are talking about a supercomputer with more than 1 gigawatt of capacity. That's literally enough juice to power a small city. All of it laser-focused on one single goal, building the next generation of AI.
And that, right there, leads us to the central question of this whole thing. Why on earth would you need that much power? Well, the answer is actually pretty straightforward. The demand for AI computation just exploded so fast that it created a genuine crisis. Google saw that its own AI workloads were on a path to literally double their entire data center footprint. Just building a slightly faster general-purpose chip wasn't going to solve this. They needed a totally new way of thinking.
And this is what they came up with: the Tensor Processing Unit. This is really the core theme of our whole story today: specialization. You see, instead of a jack-of-all-trades chip like a GPU, which has to be good at rendering video games and graphics, the TPU is a master of one single thing. It's a processor designed from the silicon up for one job and one job only: the specific math that powers neural networks. It trades away flexibility for just raw, hyper-focused efficiency. Okay, so what's the actual magic trick inside the TPU? It's this concept right here: the systolic array. Picture it like this. It's a massive grid of thousands of tiny little calculators. Now, instead of each one having to go fetch data from memory all the time, which is super slow, data just flows rhythmically through the grid, kind of like a heart pumping blood. A single piece of data gets used over and over and over again without ever needing to go back to that slow external memory. And that right there, that simple, kind of brilliant idea, is the key to the TPU's insane power efficiency. And that core idea has evolved like crazy over the years. The very first TPU back in 2015, it could only do inference. Then, V2 in 2017 opened the door to training and, critically, started linking chips together with a custom connection. But the real game changer was TPU V4 in 2021, which brought in this mind-bending optical switching technology. Now, you fast forward to today, and you've got the V6e quadrupling performance and the brand new V7 Ironwood kicking off a whole new era of scale.
Let's just zoom in on that interconnect for a second, because it's so important. With TPU V2, each chip was connected to its 4 neighbors in a flat grid, kind of like a street map. And that was already way faster than using normal networking cables. But TPU V4 took it to a whole other dimension, literally. It connected each chip to 6 neighbors and added something that sounds like it's straight out of science fiction: optical circuit switching, or OCS.
And yeah, this is where things get wild. OCS lets Google use these tiny, microscopic mirrors to physically redirect beams of light, effectively rewiring the connections between thousands of chips in less than 10 nanoseconds. Just think about that. 2 chips on opposite sides of a giant warehouse can become direct neighbors instantly. It means you can route around any chips that fail. It basically turns a rigid collection of computers into one single, massive, programmable supercomputer.
So, where has all this evolution taken us? Well, it's led to this monster: the TPU V7 Ironwood. I mean, the numbers are just staggering. 4.6 petaflops of compute on a single chip. That's 4.6 quadrillion calculations every second. It's got 192 gigs of super fast memory. And they deploy these things in superpods of over 9,000 chips at a time, delivering a mind-melting 42.5 exaflops of power. It's almost impossible to even comprehend that level of performance.
Okay, but having a Ferrari engine is pretty useless if you don't have a steering wheel, right? So how in the world do you actually program a supercomputer made of 9,000 interconnected chips? Well, that's where the software comes in. Specifically, a framework that has become the darling of top AI research labs, the JAX AI stack.
The whole idea behind the JAX stack is that it's not one giant, clunky thing. It's more like a set of Legos. It's totally modular. JAX itself is the core numerical engine. Then you have things like Flax, which gives you a really intuitive way to build the layers of your neural network. Optax handles all the complicated math of how the network learns. And then a tool like Orbax is crucial for making sure your massive training job doesn't just die if one piece of hardware fails. You just pick and choose the exact pieces you need. Now, underneath all of that is the real secret ingredient, XLA,
the Accelerated Linear Algebra Compiler. The best way to think about XLA is as a super intelligent translator. It takes the nice, high-level Python code that a human can read and write, and it transforms it into the brutally efficient, low-level machine code that the TPU hardware can execute at lightning speed.
And XLA's biggest trick, its absolute superpower, is something called fusion. So without XLA, if your code says, do step A, then step B, then step C, the chip has to write the result to memory after each and every step. It's slow. But XLA is smart enough to look at those 3 steps and fuse them together into one single operation, completely eliminating all that back and forth to memory. And that is a huge, huge deal for performance.
Okay, so we've got the crazy specialized hardware and the super smart compiler software. Let's see what happens when you actually put them together. What does this look like for a developer, and what kind of performance does it really unlock? You're not going to believe this, but this is it. This single line of code you see right here. jax.jit. You write all your complex math in pretty standard Python, and you just add this one little decorator in front of it. That's it. That's the command that tells JAX, hey, send all of this down to the XLA compiler and work your magic. It's the simple bridge between your idea and the full power of the supercomputer.
And what's the result of adding that one line of code? Well, this. This is a real-world example. Running a bunch of complex matrix operations took about 5.5 seconds. But running the exact same code with that jax.jit command dropped the time to just 1.4 seconds. That's not a small improvement. That is a nearly 4 times speedup just from letting the compiler do its thing.
And look, this isn't just about cool benchmarks or little party tricks. This incredibly tight integration of hardware and software that were designed together from day one, this synergy is letting companies achieve things that were basically impossible just a few years ago.
Just take a look at who's using this stuff. The Korean tech giant Kakao got a 2.7x boost in throughput for their language models. The creative AI company Lightrix was finally able to break through a scaling wall that was holding back their video generation model. Midjourney, they moved over from GPUs and saw a whopping 65% cost reduction. And in the world of science, a company called Escalante is designing new proteins 3.65 times more efficiently. I mean, these are real game-changing results.
So what does all this mean for someone who actually wants to build on this platform? It means you can choose the absolute perfect tool for the job. You see, the different TPU versions aren't just newer is better. They're specialized. If you're doing tons of inference and need to keep costs low, the V5e is your workhorse. If you're training a massive frontier model, you need the insane scale of a V5P or an Ironwood with those 3D interconnects. It all comes back to that core idea. Purpose-built design just wins.
And that really brings us to our final question for today. The TPU represents a massive all-in bet on specialization. It gives up the ability to do everything pretty well in order to do one thing, the math of AI, exceptionally well. So as these AI models continue to grow at this exponential rate, is this specialized path the only way forward, or will the general-purpose chips eventually find a way to catch up? It's a really fundamental question about the entire future of computing itself.